Okay, so I will begin where we left yesterday. So maybe I should give a small recap. So what we were looking at was this construction, combining and only combining so far, and the chain rule. So it should be clear how this construction is going to generalize. Every time we replicate this entire structure, okay, so these are channels. There is some echo. Anyway, can you turn the volume down a little? So you replicate it, and then there are two halves, a bottom half and an upper half. The bottom half is connected by these wires to the upper half. So this goes on and on. The algebraic description of what we are doing here is is like this. It's defined by a Kronecker power of a small matrix. So this operation here from U1 to U to X can be described as use row vectors x1, x2 multiplied by this matrix. Let's call it F. This gives us U1, U2. If we go to the size 4 construction, in the size 4 construction, the transformation is you take the F matrix and you simply do, this is the Kronecker, second Kronecker power of F. So the second transformation, the one that you see here, this part. So that transformation is you take a length 4 vector here and multiply it by this matrix. And that gives you the length 4 code word. Here we are seeing the length 8 encoding operation from a vector u of length 8 to a vector x of also length 8. That's given by this transformation. The third Kronecker power, and x, the exponent here is the length of the vector. So in general, in other words, for any length n, which is a power of 2, we have a code, and the code word is given by simply doing this multiplication operation. A little later it's kind of obvious, but a little later I will show by an example that this operation can be done in order n log n steps. There is no big factor here. In fact, you could just say n times log n arithmetic operations are needed in order to do the encoding. This is very similar to FFT transform. In the FFT transform, we have operations over the real number field, and we have a basic butterfly. This is the butterfly in the case of the polar transform. It's over the binary field. FFT is over complex or real field, complex field, more precisely. So since all the algebraic properties, shortcuts, implementation tricks that are valid for FFT, and there's a huge literature about that, they are valid also in this context. Valid perhaps more so because there are no multiplications here, it's only additions. Okay, so I demonstrated already that this type of transformation is going to achieve polarization as we keep increasing the construction size. So we were here yesterday. There is a martingale in here embedded in this construction, which helps us say very precise things about what happens. So let me show here exactly what I'm doing. Remember, we have a W channel, two binary input discrete memoryless channels, call it W. We take two independent copies of it, and then we generate a W minus and a W plus. So more precisely, W is like a channel which goes from, so this is the first channel, and we have another channel which goes from X2 to Y2. And the W minus channel is a channel whose input is X1 plus X2. This we call U1. And the output is Y1 and Y2. The W plus channel is the binary input channel whose input is X2 or U2. And the output is Y1, Y2, and U1. So these channels are, I have already drawn this picture, so let me just show it here. This is channel W, this is channel W. Here we have Y1, here we have Y2. So the W minus channel is this one. Is this one, regarding this, treating this as noise. So we may just include it inside the box. This is the W minus channel. This one is treated as complete noise, 1/2 0, 1/2 1 in probability. And then after you decode, do your decoding on W minus, you gain access to the W plus channel. And the W plus channel has input U2. U1 is now provided, after it's decoded, it's provided as an output to the second channel. This is a little fictitious because nobody will provide this to the second decoder. Exact knowledge of this one cannot be, we cannot assume that it's available. But as we said last time, polarization will help us. So since we will only send this U1 over channels whose capacity is near 1, the probability of making a decision error will be so small that essentially we don't need the help of a genie. Okay, so that's the idea. Now, let's look at the polarization, the martingale. This martingale is, it arises out of this conservation law. So I have the capacity of W minus plus the capacity of W plus. This one is equal to 2 times IW, or if you will, the average capacity here is equal to the original capacity.
Is it C? I'm confused between C and I.
Pardon me? Oh, okay. They are the same thing. C, W, this is the capacity. I use 2 different notations, perhaps. IW, this is the symmetric capacity. This is assuming that Q of 0 at the input is equal to Q of 1 equal to 1/2. Okay, so this is always true, of course. This is the chain rule. Okay. Okay, so I made the assumption that the channel is symmetric, so that we always have, throughout this presentation, we always have this if W is already symmetric in a sense, input-output symmetric, it's sometimes called. If it has some degree of symmetry, this is going to be true. So binary symmetric channel, for example, is a symmetric channel. Anyway, so now the way, okay, so the martingale approach is a tool for analyzing this. Okay, so it is, where is the martingale? Where did it come from? Well, we are generating a population of new channels. Okay, so where does what does this have to do with a random process? Okay, so what we want to do is we want to understand. Let's go on a little bit. We want to understand the fraction of channels which are extreme channels, either have capacities near 1 or near 0. We are interested in the fraction. Okay, so the distribution of the capacities. Like it is a probability distribution. When you do the normalization, we are really interested in understanding the probability distribution relating to the capacities of these channels. So which fraction lies, for example, between 0 and 0.1? This can be turned easily into a probability question. Suppose there are 128 nodes here. I pick one at random. What is the probability that the capacity is smaller than a certain number? Okay, so that's, if I can answer that question, if I picking a node uniformly at random from this population, if I knew the probability distribution, the cumulative distribution function of the various capacities here, I would be able to, that's the equivalent question, in other words. That's what I'm really interested in learning. So that's how, that's the reason why we want to put a probabilistic structure on this question, on this analysis. So with probability 1, I begin here. All my initial channels are equal to W, okay? So they have capacity equal to, with probability 1, they are at this point, 1/2 in this example. This is an example in which CW equals 1/2. Now what do I do? If the size of the construction is going to be 2, I have only one level here. Okay, so I create two channels, W minus and W plus. So, so I pretend that I pick one of these two at random. Okay, so say there is a random process, there is a random choice. It is like a random walk down a tree. Okay, with probability 1/2, you go up or down from the current node. Here we are straighted here initially. With probability 1/2, we go up. With probability 1/2, we go down. If we do that, so this equation here can be written as the expected value of the mutual information. We need to put here some other notation. So we need a time index. Okay, so the expected value at time 1 of my mutual information or channel capacity is, with probability 1/2, I go up and I get this capacity. with probability half, I go down, I get this one. Okay, so this average here is precisely the same as this one. So that's equal to I of W. I of W by this equation, by the fact that mutual information is conserved. Here I want to look at this as W0, the value of the random process at time 0. So I'm going to be constructing essentially a sequence like this, where I start at W, and then randomly go up and down. And W2, for example, corresponds to a random choice at this level. Okay, so W1 is either this one or this one. Okay, W2 with probability 1/4, it will be this, and so on. So I generate a uniform distribution. I generate a channel process, if you like. A random process where the value of the random variable at each random object at each time instant is a channel. Okay, so this is the, okay, we define this tree process for channels, and the numerical values associated with the channels, namely the mutual information terms or capacity terms, they constitute a martingale. So this is the first step of the martingale. Why is it a martingale? The expected value at the next step is equal to the present value. But let's write the next one too, because we need to martingale, when we speak about the martingale, we need to speak about another process, martingale relative to something else. So I will call them B1, B2, etc. The BI here, this is an IID Bernoulli process, IID Bernoulli half. These are the direction selectors. B1 is determining whether I go up or down here. B2 is determining what I do in the next step, and so on. They are independent. So the martingale that I'm speaking of is the following one. The expectation of the value at time n plus 1, given knowledge of the first n steps. Okay, this conditionally, now given knowledge of this, I know where I am in this tree at time n, because I'm being told whether I went up or down at time 1, at time 2, etc. So this one, this is equal to I of W n. I of W n. So for example, let's do a very small example. Say B1 equals 0 and B2 equals 1. And let's suppose that 1 means we go up and 0 means we go down. So let's calculate the expectation. Let's calculate the expectation of where I will be at time 3. Let's calculate the expectation of the capacity, IW3, given that B1 equals 0 and B2 equals 1. So we can do it by using this graph here with this. Okay, so first of all, B1 is equal to 0. That means I went down. Okay, so I'm over here. This is a W minus channel. Okay, so I took a step down. W0 was equal to W. So B1 is equal to 0. And W1 is now equal to W minus. Okay, and the next step is 1. So which way did I go? I went up, and the state here, the channel state is W2. W2 is equal to W minus plus. Okay, so now I'm going to be looking at what I'm doing in here. W3 will either be this one or that one. It will either be W minus plus minus, or W minus plus plus, or W minus plus minus. So this expression here, the conditional expectation that we see here, is simply equal to 1/2 I of W minus plus 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 I of W minus plus minus. Now, the construction, the basic construction that we have is valid all the way through. We have this basic construction, the conservation law. So the sum of the capacities of these two channels, since they are originating from a common ancestor, this one is equal to I of W minus plus. I'm writing the same equation all the time, regardless of the depth. This is the entropy conservation law. But this is precisely what martingale, being a martingale means. Okay, so that's it. Okay, so the martingale language is helpful in describing the process, but it's also a very powerful tool to say what happens asymptotically in here. Okay, so it essentially says this one. This theorem here, it just falls out of standard martingale facts. What kind of martingale do we have here? So the process I of, let's now write a different process, a numerical process. The other day with David and we were discussing whether things that don't take real values can be called random variables. So here I talked about a random process. I called the W process a random process, and W is not a real number, it's a channel. So we cannot really talk about, so we want to talk about a real valued process. Okay, so we will use this notation, I1, I2, etc. Okay, so, or more concisely, IT, t greater than or equal to 0. This is a martingale relative to the same process that we have written, bt, t greater than or equal to 1 here. What is IT? IT is defined as the capacity at time t. WT is this channel sequence. It is not really a random process, but this one is, okay, because it's real valued. So this process here, IT, okay, the process IT is bounded. Okay, so it lies in bounded. All the values are in the interval 0 to 1. So there is, let's take this as a fact. Bounded martingales converge. Bounded martingales converge. Converge with almost surely to a limiting random variable, to a limit random variable. Not only that, they will also converge in L1, which is important otherwise. So let's call the limit random variable here, in our example, I sub infinity. So there is such a random variable. It's a proper random variable. It has a distribution. The distribution of this limit shows polarization. This we can show that this only takes the values 0 and 1. Okay, so but there is also L1 convergence, which enables us to say that the expectation of IT converges to the expectation of I infinity. This is L1 convergence. If the martingale is not a bounded martingale, this is not true always. So you have to have the fact that it is bounded helps us also make this statement. What this one, okay, so the expectation of I infinity, after you show that it can only take the values 0 or 1, well, we have in fact this one too, because it's a martingale. Okay, at each step we have this. So the expectation here is simply equal to I of W. This is I of W because it is two-valued. It takes the values, well, all of these have expectation I of W. Yeah, so let me, let's do it here. Yes.
So what you used in this is that you had some kind of conservation law, right? So,
Yes.
so any transformation that sort of has this conservation law may not necessarily be the one that you have, the one x1 and x1 plus x2
Yes.
would still work, right? I mean, all this machinery would go through. I mean, if you need bounded, but if it's a binary input, then it is bounded.
Okay. Yes. So as long as you create two channels from the current node, okay, in such a way that you conserve capacity.
So what goes wrong if you just use the identity mapping?
Well, with the okay, that's a good question. I will answer your question. Okay, it's thank you for asking the question. I will clarify that point. But let me just say this one first. For every t, because we have a martingale and conservation, this is true. For all t, for every finite t, right? We begin, you can show it by induction. Okay, so because we have a martingale, if I stop at time t, my fortune, expected fortune, did I do it wrong? Yes. Yeah, my expected fortune at time t, if I stop there, is the same as my initial fortune because it is a martingale. Fine. Okay. Now, I also know the following. I of t, I'm using two different notations now. Let me simplify the notation. So this is my initial fortune measured in bits, channel capacities, and this is my fortune at time t, also measured in bits, channel capacity. So it is conserved. What else do I know? I know that this converges almost surely to a limit random variable. This is true whether it's bounded or not. As long as you have a martingale, as long as you have a martingale. Martingale meaning that the absolute value of this IT is integrable, okay? So there is some slight technical condition, but this is true very generally, okay? But this is not strong enough. Strong enough. For example, just by looking at this, I cannot say that this converges to I infinity. This one is true because it's a bounded martingale. Boundedness is a sufficient condition for this to be true. So I'm also able to say this. Okay, so these two facts are general martingale theory. They have nothing to do with the details of this construction. Okay, I'm not using any of it except, you know, as long as you have martingales bounded in 0, 1, these are going to be true, no matter what you do. Now I will answer your question. Okay, I said something else. That I infinity, okay, so let's first put these two facts together. Expectation of IT is equal to I0. Expectation of IT is not moving around, it is just staying at I0. Okay, therefore the limit is also I0. Therefore, the expectation of I infinity is equal to I0. Okay, this limit random variable, I don't know what its distribution is, but it has expectation equal to the original channel capacity, I of W. Fine. Now, how do I know that this thing is polarized, that it is either 0 or 1 valued? Now here, you said, what if I take F, my combining matrix, as the identity matrix? In other words, you are not doing anything. Okay, so this will not polarize. This is not going to polarize. So what do I need? We need to do additional work. Okay, for that, these are going to be true, but I infinity will just be equal to I of W. Okay, so the limit random variable here will simply be equal to I of W. Nothing is moving around. There is no polarization. Okay, now, so we have two things. One of them is conservation, the other is extremization in this process. Remember this inequality. We create two channels. One of them is better than the original channel, and the other is worse than the original channel. What is the condition for equality here? If you have equality in one of them, you have equality in both of them because of conservation of entropy. With equality, if and only if the channel here is an extreme channel. If and only if IW equals 0 or 1. This one is by Mrs. Berger's lemma. That's sufficient to prove this. Mrs. Berger's lemma. But it can be proven otherwise. In fact, I did it using the Bhattacharya distance. Okay, so the Z parameter for a channel, but it can be done. It can be done in many ways. Okay, so there are, and you may, I mean, any information theorist can do this in 10 minutes.
So if I can't do it in 10 minutes, that means I'm not information theorist.
You want to listen? No. Okay. Okay. Maybe I cannot do it.
It's going to be part of your qualification.
But this is something I want to skip over. Okay. So normally you have this. Okay. So unless you start with an extreme channel, in which case you really don't want to do any of this. this is going to be the case. So the channels are going to split apart. You have W here, or WT, let's say. We have a channel WT at time t, and then we look at the children, okay? So the children's mutual information or capacity are going to be separated from each other. So you have and furthermore, one can put a lower bound on the amount of separation in terms of the distance from 0 or 1. Okay, so if a channel, do you see what I mean? It is a result like this. I of W plus minus I of W minus in absolute value is greater than or equal to a result of this type, greater than or equal to delta epsilon, where epsilon is defined as the minimum of I of W and 1 minus I of W. Where this delta is a function which is strictly positive, okay, if epsilon is positive. You see what I mean? Okay, there is a result like this. It is similar to the entropy power inequality. That's also an inequality of the same sort. This is for the discrete case. There are many ways of doing this, okay? So the answer to the question is, there is a rigorous proof of this one, but the intuitive answer is the following. We know that there is this limit, IW, I infinity. It cannot settle down, the process cannot settle somewhere strictly between 0 and 1. The reason is that's not a stable equilibrium point for this process. You iterate one more step, you get splitting. Okay, so how can you have this as the limit? Because the process from any point onwards, it has children which keeps moving apart. So the only way you can have the limit, in other words, has to violate that statement. So it has to be the possible limit points of this process are 0 and 1. Okay, we can make this more precise than I'm saying now. Now, after you do that, then you have the following. Everything, then there is really nothing left. So you also, okay, so by that argument, okay, because there is separation, okay, extremization in each step, the limit here has to be 0, 1 valued. Okay, and the probability that the number of channels, the fraction of channels which are converging to perfect channels, it's this number, right? Probability of I infinity being equal to 1. This is equal to, because it is 0, 1 valued, it's equal to the expectation of I infinity, which is equal to I of W. Okay, so we have exactly the same fraction as the original capacity going to the upper limit. It is not surprising, of course. There is one further thing which I may say here in order to give some more intuition. I said, you know, a martingale converges, etc. Why does it converge? The intuition here is the following. This is 0, this is 1, and the process starts here, and there are all kinds of paths, as you see. Let's consider, you know, a point which is close to 1 after a number of steps. Okay, so it's a point like this. What do the children or the offspring of this one do? You see, as you get close to the boundary, it becomes extremely difficult to move away from the boundary because you cannot, for a child cannot do this, okay? Because the other child would have to do that in that case. It would have to become larger than 1 because there is entropy conservation. The mean has to be here, okay? So as you get close to the boundary, the steps have to become smaller and smaller. Okay, so it is like the time slowing down. You keep spending the rest of your life, most of them, near the boundary. So the boundaries are absorbing boundaries in some sense. You never hit the boundary, but once you get close to it, you cannot move out of the boundary like a black hole and strong gravitation. Some of it will escape. Okay, so there will be obviously a certain fraction which will escape. They will come back down and maybe move in the middle. Okay, so that's why the process is not so simple. And to a certain extent, it will depend on the location of the origin, the original point. Okay, so let me move. So this is already we have said. So this result here and what I have shown here does not tell you anything about the rate of convergence. Unfortunately, martingale theorems, although very powerful, there are no general, as far as I know, rate of convergence results on it. I have looked at all the books that I could find on martingales, and they were completely silent about the subject. So this proof here, the proof of this fact, is dirty. Okay, so it is not a general result, but there is also some intuition about this that I can give you. So how fast do you converge to, let's say, 0 or 1? Yes?
Go back to that picture a little bit more before we...
Which one?
The fact that you said the top and the bottom are absorbing sets.
Mm-hmm.
So what prevents you from having a significant mass kind of jumping back and forth in a limit cycle or something in the middle and never go to the 2 absorbing sets?
Okay, so well, now if you look at my answer is the following. What we are really talking about here is really strong convergence. There is weak convergence and then strong convergence. So the convergence here is strong convergence. Okay. So almost sure convergence, strong convergence, which does not allow you to go up and down, etc., indefinitely. Okay, so you have, in other words, the probability that the limit of xt as t goes to infinity equal to x infinity is equal to 1. Not limit out in here. Okay, something like this. But there is...
It has to do with the gap being the min of I of w and 1 minus I of w, right? So if you're in the middle, you polarize quickly. The gap is very large, so it pushes you towards the edges. But once you get...
His question is the following, okay, what is your question? You are asking why doesn't a significant fraction of these later on escape from the boundary and accumulate near this boundary? They change roles, in other words. A good fraction of these move up.
My question already.
Yeah.
Because you go up and down, but every time you lose something to the boundary, and then you get an exponential loss or something, then eventually you lose everything to the boundary.
But you don't. Okay, so let me also say the following. Even with processes, martingales, that are not bounded, what you say doesn't happen. It's Doorb's lemma. Okay, so the number of times you cross 2 boundaries like this is never infinite. Okay, so if you look at any book on, my recommendation for a book on martingales is this one, Williams. Okay, so he explains it. The first theorem he proves is Dupes upcrossing inequality. Upcrossings inequality.
This is R. Williams.
R. Williams.
It's Ruth. This woman, actually.
Really?
Williams.
Okay, I'm sorry. So this upcrossings inequality tells you that you cannot do these oscillations.
Yeah.
Okay, so if this were true, you could make a fortune in the stock market by, employing this buying and selling strategy. Buy low, sell high. And, the stock market will give you infinitely many chances to do so. Okay, so it's not so simple, in other words. So it doesn't occur. Okay, so anyway, let me continue on. There is also an intuitive explanation for this one too, but let's skip in the interest of time. So I would like to give, in the rest of the talk, maybe 10 minutes or so, explain how encoding and decoding take place and why they are low complexity. So this is going to be an example of encoding. So we have these channels. We have done the calculations, and these numbers here are the capacities of the channels that we've synthesized. Okay, so, and we would like to send data at a rate of 1/2. So we are going to be encoding 4 of the inputs here. We will be sending 1 bit across 4 of them, and then we'll be freezing the remaining 4. So this one has very small capacity. We freeze it. We will freeze its input. Okay, so the bit channel with the smallest capacity, it gets its input frozen as 0, let's say. And then the second smallest capacity is this one, that too is frozen. The third and the fourth smallest, they are frozen. So the remaining ones, one of them is very good. We will be sending data using it, and we'll be sending 4 bits of data across these ones. That one is not reliable enough, but that's all we can do with this construction for size 8. As the block length increases, these numbers are going to polarize, of course. Okay, and will be the probability of error is going to get smaller. So specific numbers, so the frozen bits are 0, the remaining ones are arbitrary data bits. So how we do the encoding is obvious. We will do it stage by stage. There are log n stages here, logarithm of capital N. So for n equal to 8, in 3 time units, we'll have the encoded code word. So this is a fully parallel encoding operation. We are doing it, the parallelization here is n. For n very large, you cannot really do it in parallel. Not too practical. But if you do it sequentially, how many operations, sum operations are you doing? You are doing n log n. So it's clear that the encoding complexity is n log n. This is basically like computing a Fourier transform. Fourier transform using a fast Fourier transform method. So that's simple enough. Okay, here is the example. In 3 stages, we do the encoding. Decoding is more interesting. The suggested method for doing decoding is successive cancellation decoding. I haven't mentioned it until now, but these codes have what's called the Plotkin structure, U plus V, or A plus B. In the following sense, here there is an A vector, and there is a B vector here, and the X vector here has this form. X is equal to A and A plus B. So these codes have very close relationships with Reed-Muller codes. Reed-Muller codes also have this structure. And in decoding, we take advantage of this structure. We have this A plus B structure not only at this layer, but at each layer. You also have it, the B1 through B4 here also has this sort of structure. It is the sum of this vector and this one. Okay, so it is recursively Plotkin, in other words, all the way through. So now in decoding, what we have is, we have received some y's at channel output or log likelihood ratios, and they are available. Now the decoding circuit is going to work from right to left, okay? Encoding left to right. The way I have drawn it, it will be right to left. So what we do is the following. It's a recursive algorithm. The decoding task for this full code is going to be broken into two similar decoding tasks. Okay, so the likelihoods available at these points, they will be combined to compute likelihoods for B1, B2, B3, B4. So these are going to be treated as noise. These are data bits. Let's go back. So there is an A vector here. This A vector is coming from some data and maybe from some frozen bits. We don't know what these are. If some of these bits are frozen, we know a little bit about these. We know something. But in this decoding, we don't try to take advantage of our knowledge of any of frozen bits in this segment. Okay? So we treat all of them as pure noise. If pure noise is being added to, is interfering, if we didn't have any observations about the pure noise, we wouldn't be able to do anything. But fortunately, Y5 tells us something about A1, Y6 about A2, and so on. And in fact, if these are perfect channels, you know these exactly. We don't have perfect channels, but we still know something about these. So that's some, this is valuable observation. Okay, so the B1 here is the sum, modulo 2 sum of X1 and X5. We know something about both X1 and X5 through our observations Y1 and Y5. So we combine these two observations using the same laws as we do in sum product algorithm to come up with an estimate for B1. Okay, so essentially what we are doing is we are computing the likelihood ratio for B1 using the W minus channel. Okay, so after we, so now the decoding task has been reduced. The present decoding task is the decoding of this segment, which is exactly the same as the original decoding task.
Question, after you estimate its likelihood, so you round it to 0 or 1?
After I estimate these ones, we make hard decisions. Hard decisions. So now, okay, so we have likelihoods relating to these ones. Using these likelihoods, we compute likelihoods relating to these two, using the same logic. You notice the same recursive structure here. And then there is, in fact, one more level of similar U plus B structure here. Okay, and a likelihood ratio is computed for U1. And now U1, if it is a frozen bit, regardless of what we compute, we set it to the correct value. If it is a data bit, then we select in accordance with the computed data bits. We make a hard decision. When all these are decided, they map into a unique hard decision relating to B1 through B4. And then we proceed to the next stage of decoding. Okay, so these are now known hard decisions. These things are to be estimated. Now, if these have been estimated all correctly, each of these is like having been sent through the channel W plus. Okay, so the equivalent channel here for A1 is a W plus channel. If these things have been, if B1 has been estimated correctly. I said W plus, but W plus at this layer, of course. Okay, so I have here more detailed explanation of what we are doing. Okay, so this is the equivalent channel model. So what you have here, yes, indeed, the W minus channel. Okay, so if you look at just that part of the graph, this is what you see. And then you have this copy, the third copy, and the fourth copy. They don't interact with each other. Okay, so you have 4 copies, and each one is a W minus copy. So you use Y1 and Y5 as the observation. B1 is the input to a W minus channel, and you compute the log likelihood ratio for B1 to be 0 or 1. And you do it for all of these ones. And then you go on to, okay, now use B1, B2, B3, B4, and the UU plus V structure here to compute the likelihood ratios for W1 and W2. So now W1 and W2 are effectively being sent over these channels, W minus minus.
Question?
Yes?
As you propagate these likelihood ratios, how large are they getting?
Well, they are not getting large. I mean, we do this using 4 or 5 bits of precision in the logarithmic domain. That's enough. And then finally, you have this one. The decision about U1 is made effectively using this channel and all the channel outputs. Okay, so this is the log likelihood ratio. If the log likelihood ratio you've computed, well, if the bit is frozen, you ignore this, okay, and you never make use of it. If the bit is not frozen, then you decide in accordance with the computed log likelihood ratio. After computing this, we will now compute U2, but now we are going to be assuming that this is correct. So we have this structure here, we compute the log likelihood ratio, and it goes on like that. Okay, so this is an algorithm whose complexity is n log n as well, and the martingale convergence theorem with the rate of convergence, together with the union bound, gives us this result, that the probability of decoding error goes to 0 exponentially in the square root of n for any rate r less than the channel capacity. So there are 3 types of complexity in order to call something a capacity achieving with low complexity. Construction complexity is also important. I talked about encoding and decoding, but what is the construction complexity? How difficult is it to find the positions, the proper positions for the frozen bits? Okay, so that is a result that came out of a succession of work starting with Mori Tanaka, Tal and Varde, and the last word was said in a joint paper by all these people, and he is not here, I believe, but Ramtin did also. He proved beyond any doubt that this is a polynomial time algorithm. This, okay, in a paper with several authors, this result was proven. Ramtin Pedersani and several other people from EPFL. I'm sorry, I don't remember the exact names. So you have a code for which the construction complexity is almost linear. Encoding and decoding complexity are n log n, and there are no big constants in front of these. They are basically n log n. Okay, so and then the frame error probability goes down exponentially. So I want to conclude this by showing something about performance. Now the and these are the least decoder result here is due to Tal and Vardy. These are results that I have presented before they did in 2011 at ISIT in St. Petersburg. So it's the same slides. If you use list of size 1, which is the successive cancellation decoding algorithm that I have mentioned, this is what you get in terms of performance. If you use a list decoder with list size 2, I won't have time to explain exactly what this means, but essentially the list decoder, the weakness of the successive cancellation decoder is that if you make a mistake, and you are prone to making mistakes if you are aggressive about using the channels, those channels which have not yet polarized sufficiently, if you use them, you are prone to making an error there. That's the weakness of the successive cancellation decoding algorithm. So how do you take care of it? The list decoding idea, I should also mention the name of Ilya Dumer, because he came up with this list decoder in the context of Reed-Muller codes, maybe 15 years ago. Okay. The idea is the following. You don't, so you follow both possibilities. You don't commit yourself to either 0 or 1, but you follow both possibilities. This is important, especially at the decisions which are bound to be unreliable or semi-reliable because the channel that you are using is not sufficiently polarized. You want to still use them, otherwise you lose too much from rate. Okay? So if you use a list 2 decoder, there are many variations, so the details are not so important. So essentially you keep following 2 branches and then keep the best 2 all the way through to the end. And at the end you select the better of the 2. You get a significant performance improvement, as you see here. List of 4 gives you further improvement, 8, 16, 32. And in fact, when you get to list size 32 or so, you are at the ML limit, okay? The reason why this thing saturates here or settles down to some floor, this is not an error floor, but it's a floor, is because, you know, that's the ML bound. You cannot go below it, no matter what you do, because in the end you select only 1. Okay, so Vardy and Tal's main good news was, you know, not the list size doesn't really have to get astronomically large to achieve the ML bound. Okay, so with a reasonable list size, you get down to the ML bound.
A question here.
Hmm?
So actually, we see error flow for high rate codes like starting from rate 0.8. Now, like if you go back to the previous slide.
Yes.
Yes. So here the result you are showing is for rate 0.5, right?
Yes.
And so I recently started working on polar codes. Mostly worked on LDPC before. And the complexity is still much more complex compared to the LDPC, like not in terms of the more in terms of the gates. But we're very interested in terms of the seeing where we are in terms of the polar codes. So we're looking both at the.
Okay, let's discuss this after, because I'm in a hurry to finish, so that we don't hold people here. I will finish in 2 minutes, I promise. So this thing is due to the poor minimum distance of the polar code. Okay, so the reason why it hits this sort of error floor, let's call it error floor, because the minimum distance grows only as square root of n. When I am saying only, you know, it's still much better than LDPC codes, which aggressively try to achieve capacity, because there the minimum distance goes to a finite number. Okay, so still this is going to keep going down like that. Okay, but it goes down with the square root in the exponent. So how can you fix this? The answer is you need to improve the minimum distance of the code to improve this. So Again, Tal and Vardi, they suggested using a CRC, a concatenation basically. The CRC is going to help improve the minimum distance. And when you improve the minimum distance, list decoder with a 16-bit CRC, it achieves as good performance, if not better, than turbo codes and LDPC codes that are used in WiMAX. Okay, so this one is the list decoder performance. This is list plus CRC 16 performance. And these are performances of turbo and LDPC codes that are used in WiMAX. Okay, so there is, of course, a lot more work that has been done since then on practical side of these codes. In summary, this is the summary. Okay, so we not only have a family of codes which achieve the Shannon limit, but also if we supplement them with some other methods, they have the potential to be useful. So thank you for your attention, and if you are interested in this presentation and some other notes, you can write to me, or I will leave this here so you may perhaps be able to copy it as well. Thank you very much.
Thank you very much.
Thank you.
Any questions?
Can you explain the intuition of the sub-exponential convergence rate?
Okay. So the reason why okay, so that's not, I said it's intuitive, but it's not so easy, in fact. I mean,
Intuitive to you.
so if you take the logarithm of this process, not this one, but the log of this one, it behaves as a random walk, okay, with which either stays where it is or moves down one step. Okay, so half of the moves are tell you, stay where you are. The remaining half point towards the boundary. Okay, so that's the main reason. So basically, this is a process with two attractors. You define, let's say, a process like this. Okay, now it has only one limit point, 0. Okay, and then you take the logarithm of this one. This process is approximately a process which is either 1 or 0, with probability a half, with probability a half. Okay, so this is the basic intuition. So convergence to 0, in this case, it means, what does it mean? It means going to minus infinity. Okay, so a process like this can go to minus infinity only if, half of the steps are not moving you at all. So the rate at which you go to minus infinity is, so for a construction size of capital N, you take small n steps, logarithm of n steps. Half of these, so log n, this is the number of steps. Only half of these steps are useful steps for convergence. The remaining ones are keeping you where you are. Okay, so that's the intuition. Okay, so
Okay, all right. So we've succeeded. Oh yes,
So,
Venkat.
yeah, so that explains that it can't go faster than 2 to the minus.
yes, no way.
It goes to 2 to the minus root n. Is there any explanation other than the
Huh?
Bhattacharya calculation?
Pardon me?
So this explains that it cannot go faster than 2 to the minus root n.
Yes.
But the fact that it does go with 2 to the minus root n, so the proof using the squaring of the Bhattacharya parameter, is there some intuition to explain that? Other
So
than-
I must also say the following. Right? These things are true for binary channels. So if you go to larger alphabet sizes, the exponent there improves. And in fact, the rate of convergence with increasing alphabet size goes to n. Okay, it becomes linear in n. The square root gets replaced with large alphabet sizes. It becomes. Is it clear what I have said?
So do you mean large alphabet sizes or large kernels?
Not okay, both of them, in fact. So there are two things you can do. We've been using, a kernel of size 2 by 2. If you replace this with larger kernels using the binary alphabet, as this thing gets larger and larger, I mean, it's kind of obvious that you can stick in here anything you want. Essentially, you may have a very powerful code in here as your kernel. Then the exponent here is going to improve to n. Okay, so but there is another line of work using small kernels, non-binary codes, especially codes that originate from Reed-Sullivan codes. So again, Mori and Tanaka, they did the initial work on this. They showed that the exponent, let's call the exponent here 1/2. Okay, so the square root, call it 1/2. Okay, so Mori and Tanaka have shown using a kernel of size 4, I believe. So you can look it up. They show that the exponent improves to something around 0.7. Okay, instead of square root n, we are now talking about this number, n to the power 0.7. So both avenues are open, in other words. However, things get more complex. So here, if you go to query alphabets, you must be doing this sort of essentially belief propagation on a query alphabet. Okay. If you use this structure, a 2 by 2 matrix, even if you increase the alphabet size, you cannot do any better than this. This is what we are referring to. So this kernel here, you may put alpha, beta, gamma here for a larger field size, but this is not going to improve performance. You will still have square root of n. For binary alphabets, let me say this too, and then I will stop. If you restrict the alphabet to binary, and you look at larger and larger kernels, Korada, Shashoğlu, Urbanke, they have shown that things are not going to get any better until the size of this f, the kernel, becomes larger than 32. Okay, so that simply says that it is not practical. For binary case, for binary alphabet, we are using this 2 by 2 kernel. Unless you go to a kernel of size 32, the exponent here does not improve. In fact, it gets worse. Okay, so for example, you go to 3 by 3 kernels, it gets worse. Yeah. Well, thank you very much.
Thank you. Thank you.
Thank you.